Nuclear weapons. Something that really excites us as kids until we realize they are the best way of destroying humanity and everyone you and I love. What are they made of and what makes them so frighteningly powerful? Well, to understand this, which is always the goal at this channel, we have to acquaint ourselves with a few new concepts. Fission, the splitting of atoms; fusion, the merging of atoms; critical mass; and isotopes. I'll make sure you understand how the mass of less than a gram could cause such shiver when we hear the name of Hiroshima. But what does it say? What does it mean? Let's find out. We must start with the basics. What are thermonuclear and atomic weapons? It's important for me to explain the difference between the two, because both are classified as nuclear weapons, so you might think that they're basically the same, but one is much stronger than the other. In a nutshell, they rely on different energy processes that created the gigantic explosion we see. Atomic bombs, like the one in Hiroshima, are fission bombs that split highly enriched uranium-235, or these days plutonium-239. The bomb used to end the Second World War created energy equivalent to 15,000 tons of trinitrotoluene. That's nerd language, and you probably know it as TNT. So that was atomic weapons and fission. Now what are thermonuclear weapons? That's a cooler name. Well, you've probably heard of the Tsar Bomba, the biggest man-made explosion in history. It was a hydrogen bomb, the type of thermonuclear weapon. This one relies on both nuclear processes, so it's a bit more complicated. But the main part of the energy comes from fusion this time, and it is way more efficient. And in this case, also way more devastating. Well, how devastating are we talking? Let's use the nuke map. Here's my hometown of Malmö, and let's detonate the atomic weapon used in the Second World War. Okay, so most of my friends and family is dead. Here you're barbecued by a fireball of plasma. Here your building will collapse and you will die. Here you will be forced with radioactive damage and you will die. Here your building will also collapse and you will die. And here you'll get burned so bad that you wish that you died. That's pretty bad. It's pretty bad, but some people will survive at least. My drug dealer down in Trelleborg, he's gonna survive. And the people over here at the Fasterboholms. Yes, that's where people are. But now, let's detonate the thermonuclear weapon, the hydrogen bomb, Tsar Bomba. See what happens. Okay, that's nice. So, now everybody's screwed. There's no chance of surviving that. It helps my drug dealer. Yeah, no, my drug dealer is also toast. That's very sad, very sad. But the good part is, Denmark is also screwed. So, even Steven. Good work, Noah. I hope I didn't scare you to death. Yet. Because the craziest part is still in front of us in cosmic history. But let's turn now to the physics of all of this. First up, fusion. As I mentioned before, this is the main source of energy in the thermonuclear explosion. The reason why it is called a hydrogen bomb is quite straightforward. You see, they use two isotopes of hydrogen, deuterium and tritium, to form helium in temperatures as hot as the core of the sun. What's an isotope? Well, it's still a chemical element with a certain number of protons and electrons, with a different amount of neutrons. And neutrons is the key to nuclear reactions because they initiate the fission. But we shall come to that later. Back to the hydrogen bomb. You may ask, where does all the energy come from? Well, imagine this. This isn't reality, it's just a thought experiment. Imagine you have a deuterium atom. It contains 10 joules, a little bit of energy. And then you have a tritium atom, which contains, let's say, 90 joules. Add them up, and you have 100. Wow! Congratulations, you just passed elementary maths. But you see, when they fuse together to create helium, you would think it would contain the sum of the energy, 100 joules. But no, reality is different. The helium in our experiment only has 50 joules. Half of it's gone. So where did all the other energy go? Well, that transforms into X-rays and gamma rays, which is really energetic light, or in nerd language, electromagnetic radiation with an incredibly short wavelength of 10 picometers. And that can create plasma, give severe burn damage and cause mass extinction, especially of us humans. And this is what makes thermonuclear weapons capable of destroying civilization in a day. Let's move on to fission. Here neutrons are used to split atoms in two. Picture a really big billiard table, and the white ball is the neutron. In an atomic weapon, we basically shoot it really fast and split the balls to release energy. Now when you have enough balls, and we can forget about the friction in this case, they can keep bouncing around and splitting more and more atoms. And when it can do this on its own, when the nuclear reaction is self-sustaining, when the balls keep bouncing and creating havoc without me interfering, it has reached the so-called critical mass. We usually decide to use plutonium-239 as the billiard balls in this case, because when we split this atom, when fission occurs, it releases both a lot of energy and also neutrons that keep the reaction going. When it keeps going, it eventually creates a big explosion, which in turn leaves a lot of quite dangerous radioactive material, which happens to be the topic of my next video. Now, can we do anything else with these energies than bombing people? Well, yes. Nuclear plants build upon the principles of fission and radioactivity and serves as a controversial but efficient energy source for society. What about fusion? You said that it released even more energy, right? Well, yes, that's right, but it's also a lot more complicated. Our sun, the thing which burns you and gives you cancer if you let it shine on you for too long, and is the absolute foundation of the Earth's ecosystem in history, gets its energy from fusion in the core. That's because it can only happen at extreme temperatures and pressures, tens of millions of Celsius, and that's what makes thermonuclear weapons complicated. But if we can create similar conditions as the core of the sun, here on Earth, then we can create unlimited energy supply from normal drinking water. Strong electromagnetic fields from superconducting magnets or highly concentrated laser beams are today used to try the experiment. The most important project dealing with this right now is the ITER. I suggest you go check it out. Don't forget to like, hit the bell, comment and subscribe. Have a nice day. Peace.